Hello pre-calculus students, these are your notes on parent functions and transformations. So first we have a list of parent functions. You should see how many of these you remember before watching the video. They are also in your online textbook on page 45. So taking a look at the first one, y equals x squared, if you forget what it looks like, you can build a table of values with x and y. So your x's could be negative or positive. Oops, I've lost my pen. So for x's I could put -2, -1, 0, 1, or 2. And when you square those numbers, you get these numbers. You get 4, 1, 0, 1, and 4. So -2 squared is 4, -1 squared is 1. And then once you see this, you might remember that this shape is called a parabola. It's kind of a U shape. Okay, and because of these arrows, your domain is from -infinity to infinity. Your range starts here at 0, and it goes up to infinity. Okay, next one. X cubed. So you have x values and y values. You can actually choose the same values. -2, -1, 0, 1, and 2. When you cube it, if you raise it to the third power, the -1's going to stay negative. -8, -1, 0, 1, and 8. So some of these don't fit on the graph. Let's see. 1, 1, and then 2, 8. But just because I really want the general shape to be about right, I'm going to estimate it's going to be about here somewhere. And then -1 and -8, and I'm going to estimate that one to be down there somewhere. So your x cubed is going to look something like this. So your domain is also -infinity to +infinity, but your range in this case starts at -infinity and goes to infinity. Okay, square root function. We cannot graph the square root of a negative number because those are imaginary, and the imaginary numbers don't show up on our graph. So I can square root 0. That's the first one I can square root. So the square root of 0 is 0, and the square root of 1 is 1, and the square root of 2 is irrational. That would be hard to graph. So I'm just going to go to the next number that's an easy square root, and that would be 4. The square root of 4 is 2. So I'm going to graph 0, 0, 1, 1, and 4, 2. And this is your graph. Make sure you get all those points on your graph. Your domain starts at 0 and goes to +infinity. And your range starts at 0 and goes to +infinity also. Okay, cube root. So again, just like we chose values for x that we could square root here, we're going to choose values for x that we can cube root. So I can cube root 0, that's 0. I can actually cube root a negative number. The cube root of a -1 is -1, and the cube root of -8 is -2. And then those values are mirrored in the positive. Okay, so notice these points here are the same points that we had in the cubed, but then the graph looks a little bit different. It gets a lot flatter. So I'm going to go estimate out to 8 and 2, and the reason I'm doing that estimate is because I want to see the difference between this graph and this one, and estimate out to -8 and -2. Okay, and once more, we have a domain from -infinity to infinity and a range from -infinity to infinity. All right, the rational function is a tricky one because it has some asymptotes on it. So let's choose a new color. You cannot put 0 in for 1 over x, because if you do, you're dividing by 0. So that's going to create an asymptote at x equals 0. You can also not get 0 as an answer because there is no number you can put in for x where 1 divided by 0 will give you the answer. So there's no y value at 0 either. Okay, so if you chose a table of values, you might choose numbers like -2, -1, 0, 1, and 2. And when you plug them in for x, you'll get -1/2, -1, 0, 1, and +1/2. So we're going to graph -2, -1/2, -2, 1, -1. 0 does not work actually. 0 you cannot plug in. 1, 1, and 2, 1/2. And you end up getting the graphs of the branches of your rational. So these are these curvy L-shaped graphs. And we're going to have a whole unit on rationals later, but for now we just wanted to look at that parent function. So your domain is everything except for not this x here. So you would say -infinity up to 0, don't include the 0, and then 0 to infinity. And your range ends up being the same thing, -infinity up to 0, and then 0 to infinity. Okay. Number 6 is your constant function, y equals a constant. It could be any number you want. So say I decide to put in 2. If I have y equals 2, then that would go across here, where all the y values are 2. And so then your domain is all real numbers, -infinity to infinity. But your range is just a single number. It's the number where you chose to put your graph. So you could say that it's a constant, or you could say in this case that it's 2. And remember, that's just the special case that I chose. It could have been any constant. This is called the greatest integer function, and we're going to come back to that in just a second. Greatest integer. Let's do the absolute value one first. So the absolute value is the distance a number is from 0. So -2 is 2 away from 0, -1 is 1 away from 0, 0 is 0 away from 0, and you can see. So a lot of people just think of absolute value as changing any number to positive. If it's positive, it stays positive. If it's negative, it goes positive. But literally, it is the distance a number is from 0. So let's graph those points, and you see that this shape is a V shape. So your domain is -infinity to infinity. That's from here to here. And your range starts at 0 and goes up to infinity. Okay, the greatest integer function is defined as y is the greatest integer less than or equal to x. So if we make a table of values, if x is 0, the greatest integer less than or equal to 0 is 0. But you want to go to some decimal values like 0.5. The greatest integer less than or equal to 0.5 is 0. Anytime you put in an integer, the answer is going to be itself. And anytime you put in a decimal, let's put in 1.5, it's going to be the integer before it, 1. So your y values are only going to end up being integers. So what you end up with is you'll have a point at the integer, and then it will continue being that y value until you get to the next integer. So you have an open dot here. You have a point at the integer, continue getting that y value until the next dot, and then you have an open dot there. It's a little bit hard to write with the big pens on here, but you get the idea. And it continues down to the negative values as well. Okay, so this graph continues. So your domain is going to cover all the numbers. You can put any number in for x. Negative numbers, positive numbers, no problem. But if you look at your range can only be integers. None of the numbers between the integers are included. So there is a letter that we use for all integers, and you can write all integers. But you can also say that y is an element of z, and z stands for all integers. Alright, so in the next section you are invited to graph these on your calculator. When you're graphing them on your calculator, you need to press y equals, and to get the absolute value you would press math, and you would go right in order to choose num, and it looks like this on your calculator, ABS like this. So then you would press that, and some calculators, they give you the absolute value, so it looks just like this. And some calculators, it actually says ABS with the parentheses, and then you'd need to remember to close the parentheses when you're done. So take a minute to pause the video and try graphing these to see how this absolute value function changes when you put these changes in. And I'm actually going to add a number 19 down here. So number 19, I want to see what happens if I put a fraction inside the absolute value. So say I put in, doesn't matter, 1/2. Okay. So what's going to happen to your V shape? Remember, here's your parent graph. If you put x plus 1, your V shape is going to move left 1. And if you put minus 2, it's going to shift right 2. So notice that anything that happens inside the absolute value happens inversely. It says plus 1, but it actually goes left 1. It says minus 2, but it actually goes right 2. And that's going to happen down here for the 19 as well, but we'll talk about that in a minute. This one here happens outside the absolute value. So it's going to be different. It's going to move the graph up instead of left or right. And then this one's going to move the graph down. Okay? In number 13, you're going to see 2 shifts happen, and by this point you might be able to predict it without graphing it. You noticed over here x minus shifted the graph right, so this one will move right 4. And then this one will move up 2. The x plus, you'll notice over here, it shifted left, so that was left 3, and then this one is down 4. And then this one, you're going to notice 2 things with this one. For number 15, when you graph it on your calculator, your graph is getting taller and skinnier. And because the absolute value is really made up of 2 linear functions, it actually does not matter if you think of this as making it taller or skinnier, but for some functions it does. So we're going to try to apply the rules. If it's outside the absolute value, outside, then it's changing the y values. So by changing the y values, we're pulling it taller. So we're going to say that this is stretched vertically by 3. And here, when you see this one, you're going to see that it got both shorter and wider. But because it's outside the absolute value, we're going to say that this is affecting the y values, so it's going to be compressing it vertically by 1/5. Alright, in 17 you have a negative that is outside the absolute value. And what that does is it reflects the absolute value graph across the x-axis. So we're going to say that this one reflects vertically, up and down. And 18 is interesting because you don't notice any change. Some people understand that you don't notice any change because the negative in the absolute value doesn't really matter since everything turns positive. What's actually happening is that your graph is reflecting across the y-axis, so that when you reflect the left side over to the right, it actually looks the same. When you reflect the right over the left, it looks the same. So in this case, the graph looks the same, although what's happening is you are reflecting horizontally. But you can make a note that this is actually the same graph as the original. And number 19 is the one I added. So number 19 has kind of the same effect as number 16. You can see that the original graph got shorter and wider. Not quite as short and wide as this one because that one was 1/5. But in this case, it's inside the absolute value. So if it's inside the absolute value, we want to say that this is affecting the x values. And remember how a +3 actually shifted left 3? Whatever happens inside the absolute value happens inversely. So you can see that horizontally, I'm not getting compressed, I'm actually getting stretched. This is a horizontal stretch. So it's not going to be multiplying my x values by 2, it's by 1/2, it's going to be multiplying my x values by 2. So this is stretching horizontally by 2. So if it's inside the absolute value, we're going to say that it's going horizontally, affecting the x values, and it's going to be the reciprocal of this number. All right, let's turn to the next page. So here we're going to try to write the equations of some of these transformations. Here's my parent function for the quadratic, x squared, and I can remember that my domain was -infinity to infinity, and my range started here at 0 and went up to infinity. So for the transformation, I'm going to go right 1, 2, 3, 4, 5, and down 1, 2, 3, 4. So right 5 and down 4. But there's also a stretch, you see, because here's my vertex, and normally my parabola would go right 1 and up 1. You can see that instead of going right 1 and up 1, I went right 1 and up 2. So this is being stretched vertically by 2, and I'll put that 2 right there. My domain is still -infinity to infinity, but my range has shifted so that it starts down here at -4 and it goes up to infinity. Okay, this function, the vertex shifted here, so it shifted 1, 2, 3, so that would be x plus 3. Notice the squared, that's from the parent function. And then it shifted up, 1, 2, 3, 4. All right, normally my graph would go over 1 and up 1. Now it's going down, so that's going to result in a negative number here, but what negative number I need to figure out. Normally it would go over 2 and up 4. This one goes over 2 and down 2. So it's going down half as much as it should. So this is going to be a compression of 1/2. My domain for every quadratic is -infinity to infinity. The range starts down here at -infinity, and it goes up to 4. All right, here's my absolute value function, and you'll remember the domain is -infinity to infinity, and the range is 0 to +infinity. So my transform function, let's see, it's going to go left and down. So 1, 2, 3, left, x plus 3. And then 1, 2, 3, 4 down, -4. Normally this graph is going to go over 2 and up 2, but it goes over 2 and up 1. So that's half as much. And I'm going to put the 1/2 there. My domain is still negative infinity to infinity, but my range starts down here at -4. Okay, and for the last one, my vertex shifted from 0, 1, 2. So it shifted 2 to the right, and then 1, 2, 3, 4, up 4. Now it's reflected, so it turned upside down, and it's stretched by 3. 1, 2, 3. So -3 here. Your domain doesn't change for this function, but the range does. So it's from negative infinity up to 4. Okay, and we have a few more here to graph. Alright, this is a transformation of my quadratic. So the quadratic usually has a vertex at 0, 0, but it's shifted down 1. Once you shift the quadratic, you just have to think of the key points on your parabola. It's over 1, up 1, over 2, up 4, over 1, up 1, over 2, up 4. And that's what you're going to count. Over 1, up 1. Go back to your vertex, over 2, and up 4. From your vertex, over 1 and up 1. From your vertex, over 2 and up 4. And sketch that in. Your range starts down here at -1. Okay, here's a cubic function. The cubic function usually has a midpoint at 0, 0, but it's going to be shifted up 1, so it's here. And it's stretched by 2. So normally your cubic function is going to go over 1 and up 1, but because it's stretched by 2, you're going to go over 1 and up 2. So from your vertex, over 1 and up 2. From your vertex, over 1 and down 2. Now if there was room, your next point would be over 2 and up 16, because that's twice 8, but there's no room for that, so you just need to try to draw your shape in accurately, like this. Okay, so the domain is still negative infinity to infinity, and the range also from negative infinity to infinity. Alright, 24 is a tricky one. The square root function, you'll remember, looks like that. And starts at 0, 0. So because of the plus 1, I'm going to go left 1. Now, normally the square root function will go over 1 and up 1. And over 1, 1, 2, 3, 4, and up 2. Like that. But because of the 2 in here, your x values are multiplied by a half. So instead of going over 1 and up 1, you go over a half and up 1. So over a half and up 1. And instead of going over 4 and up 2, you go up over half as much. So you go over 2 and up 2. Okay, so notice that this 2 here multiplied your x values by 1/2. It did not change your y values, so it didn't change how much you went up. Your domain is going to be -1 to infinity, and your range starts here at 0 and goes up to infinity. Okay, the last one is a rational function. The x plus 4 is inside the function, so that's going to shift you left 4. 1, 2, 3, 4. So your asymptote that was at 0 is now at -4. If you were going to shift up or down, it would be here. But there's nothing there, so we're not shifting up or down. So that means that your other asymptote stays right here at y equals 0. Now from there, you would normally have a point that's over 1 and up 1, like right there. But because of this 3, everything is stretched both directions by 3. So your actual points are going to be over 1 and up 1, 2, 3, and over 3 and up 1. So from where the asymptotes cross, over 1, up 3, over 3, up 1, and draw your branch in. And then do that down here as well. So you're going to go back 3 and down 1, back 1 and down 3, and draw that branch in. Your domain is everything except for -4. And your range is everything except for 0. Okay, so after this, in class we did a jigsaw activity where we took turns teaching each other some transformations of the different functions, and that one is right now available as a PDF, may possibly be available later as a video, we'll see. So please make sure that you complete your roller coaster activity after this.